So the question in my title, why focus on geology? Well, I think Jim gave us part of one answer to that when he more than once said you can't punch enough holes in the ground. And I don't know about most of you out there, but to me that was bad news, you know, to see a regulator support something like that. And you know, to consulting firms, now that could be good news. That's maybe a lot more revenue. But to responsible parties, that's potentially a lot more cost. So I think my presentation is going to generally be good news, because what it's about is how we can use more advanced geologic concepts to take existing data and define the geology. And the geology is really the subsurface plumbing. You know, so that's the one thing that this conference is on, remedies, and what all these remedies have in common is you got to deal with the subsurface and the complexities of the subsurface. You know, Jim said it's dark down there, and it's always more complex than we think the subsurface is. So, but one thing about it is that geology is static. So a better understanding of that plumbing, that subsurface plumbing, it was there before the release happened. And then, sure, there's a lot of changes in conditions down there, but the geology, no, that's static, that stays the same. So my talk is going to go along the lines somewhat of my career path. Like Jeremy mentioned, I started in the petroleum industry, but then back the last time that oil went below $20 a barrel back in 1986, that's when I lost my petroleum job and went into environmental consulting. I've been doing that ever since. But that experience, you know, had a huge impact, and my focus in my career has been to bring better geoscience to our industry. So an outline, I'm going to talk about why geology's been marginalized in our environmental consulting industry, and why does geology matter, and how we can unleash the power of existing data using more advanced geologic technology and methods in our industry. And I'm going to show that with a case study. So, yes, this is a quick review of our industry. In consulting industry, environmental consulting, it grew out of engineering firms. And so a case in point is how we define the subsurface. The standard is using the Unified Soil Classification System. And as this slide shows, it was developed for engineering purposes. So it doesn't maximize really the information, geologic information that we have available in the subsurface. So that's one example of how geology, just in the way our culture in our industry evolved, you know, has been marginalized. It's very first is how we describe the materials in the subsurface. It's way more engineering based, but I'm going to show you, that might be bad news, I'll show you some good news on how we can extract a lot of good information from old data. And the other part that's, another aspect that's traditional in the way we address the subsurface is more of a focus on hydrogeology, and really little to no emphasis on depositional environments and their related permeability architecture that, again, controls the plumbing of the subsurface. So what this shows us, okay, here is that on a lot of projects, the standard for trying to describe and understand what's going on in the subsurface is to use the simplifying assumptions of homogeneous and isotropic conditions. And that's where most of our sites, the way we designate how contaminants move and the way we predict that is usually by creating first a groundwater gradient map, mapping out, posting groundwater elevations, contouring the elevations, developing the gradient, and then estimating flow direction. And as we're creating those maps, those are all really with that underlying assumption of homogeneous isotropic conditions. And then we take our chemistry data, and based on this understanding, that's how we will map out our contaminant plume, okay? But, you know, what we know, and that works great to a degree, only to the degree where the subsurface is complex enough where these assumptions are no longer true. And this is an example that I'll show in my case study. And so the way this has evolved is it's created a problem of ignoring aquifer heterogeneity by, again, oversimplifying the way we evaluate subsurface data. And again, the geology, if we understand it in detail, it actually maps out the permeability architecture. Now, what we see on the left in this example that I'll show in my case study, this is a TCE plume that's shaded based on higher concentrations, the darker the blue. And this was the site the project site. And then, as I showed in the last slide, groundwater contours were constructed. And then based on that, this is the source area, are these white arrows, which represent the contaminant migration pathways. And based on this white arrow shows that this on-source area is the up gradient and probably the source for this, what's considered anomalous increasing concentrations of TCE. And what we'll see after we look more closely at existing data and define the geology in more detail is that, in fact, there's actually a channel. This is a channelized depositional environment, and in fact, the flow, contaminant flow, is really coming from a potential off-site source, and which makes, and we'll see why this makes much more sense based on the contaminants you see. So, yeah, so again, when we draw these white arrows, these flow directions, they have huge impacts on our projects. That's how we define where our monitoring wells are going to be. It's how we define what remedy and how we're going to implement a remedy. And it's all based on what Ron brought up, our original conceptual site model, our original understanding. And again, there's a lot of uncertainty in the subsurface, so our job is to try and reduce that uncertainty. And what I'm trying to infuse here is that, you know, a geologist is the one who could help most as far as defining, again, that plumbing system and help reduce the uncertainty of the subsurface. Now, this is an example on how geology matters. This was the 2013 National Research Council report on alternatives for managing the nation's complex contaminated groundwater sites. And just to summarize, I identified over 126,000 groundwater impacted sites throughout the U.S., and that over 10% of them, or 12,000, are considered complex. And they point the finger that it's this inherent geology complexities that's the primary reason for these challenges and not being able to get restoration, okay? And I really think this is a lot about a symptom of what I introduced, and that's our lack of focus on geology with the data sets that we collect in the first place. And now I'm just going to, again, this was part of my career path, and this is what I got exposed to early in my career, is in the oil and gas. In the early days, geologists were just out there to find the oil. And then the challenge after that was getting the oil out of the ground, not getting the oil out of the ground, handling the oil in the facilities on the surface. So it was mainly an engineer focus until these fields started in decline. And then from an economic point of view, it became increasingly important to better understand the subsurface. And that means over the last several decades, petroleum industries have invested billions of dollars in research and development on the stratigraphic controls of fluid flows. In that industry, they do the same thing as us. It's about understanding the fluid, and extracting fluids from the subsurface. But again, on a different culture that was based on, the focus there is understanding in detail, the best you can, the geology first, the plumbing first, and reduce your uncertainties as best you can of the subsurface, and then implement the important engineering remedies to take care of extracting fluids. And just as an example, the AAPG, which I've attended a handful of times, that's American Association of Petroleum Geologists. Their annual convention attracts more than 7,000 attendees, and most all the presentations and what you see there are stratigraphy. It's about geology. And again, they're doing the same thing. They're trying to understand how to get fluids out of the ground. But you go to environmental consulting conferences, and maybe you get a handful of presentations that are focused on geology, on understanding the subsurface. So again, I think I'm bringing good news, because I think what we've had in the past is a missing step, and this missing step is focusing on extracting good geologic information from our existing data. And as an example, environmental sequence stratigraphy, the sequence stratigraphy is one of the sciences that was developed in the petroleum industry over the last several decades. And what I'm showing is how we've taken the concepts of that, of really focusing on understanding depositional environments and facies models in order to take the data that we have and be able to develop a more detailed understanding, be able to predict, and hopefully reduce the number of holes we need to punch in the ground, because we're able to do a better job predicting what's in the subsurface, the plumbing in the subsurface in the first case. And that involves these three steps. The first is understanding depositional environment. That's the foundation of how the geology and the subsurface was built and deposited. The second part of it is leveraging our existing lithology data by formatting and to emphasize vertical grain size trends. And for a stratigrapher, that's like the Rosetta Stone. That's how a stratigrapher is able to connect these vertical grain size patterns to depositional environments, and then be able to make valid predictions between our known data points. And then lastly is to actually map out the permeability architecture. Again, that's what the geology is. It's being able to map out and predict our contaminant migration based on that. And by the way, probably the most important component of this whole thing is the practitioner. You really need a trained stratigrapher who has an encyclopedic knowledge about depositional environments, and then also, again, a lot of practice in understanding how to interpret the vertical grain size patterns. So just as an example, what I was talking about is you need to relate the depositional environment to our existing lithology data, and that's primarily pattern recognition. Examples here you have a lake, you have a river depositional system, you have alluvial fans, glacial, and then offshore and beach deposits. Well, all of these have characteristic vertical grain size patterns that have been established through all the research done primarily in the petroleum industry and also in academia. And so what I'm going to show in my case study, the example, is how we can use the data that we collect to identify these grain size patterns when you understand the depositional environment and put together valid subsurface maps for us to be able to then design our remediation programs, our monitoring and remediation programs. So that's why I'm saying it's not too late for us to fix this problem. This missing step is available for us to do today, and that's because we have these existing, really, in a vertical sense, high-resolution data, whether it be boring logs, CPT logs, or geophysical logs. But again, they're not being being used to the full capacity. And what we typically do in our industry is, again, focus on that USCS. And we'll create our cross-sections by first setting up strip logs of our USCS description, like you see here. But what I mentioned is we're able to extract a lot of valuable information by looking closely at the boring logs and focusing on grain size, and then mapping out, I call them graphic grain size logs, where you map out the coarsest grain fraction farther to the right, and the finer grain fraction, like clays, closer to the axis. And this is where you're able to then, like I mentioned, make it these visual representations of vertical grain size patterns. And for instance, one thing that sticks out right here is you got an SM or silty sand identified both here and here when you just look at a USCS log. But when you look at the more detailed the grain size, you see that you actually have differing and finding upward grain size patterns. So environmental sequence stratigraphy, the whole beauty of this approach is that the data is already paid for, because we're talking about looking at existing lithology data at our projects. And the oil industry has already invested billions of dollars into this technology. So it's transferring it by, again, getting the experts, the practitioners, the stratigraphers to reevaluate the data that we've already collected on our projects. So if you understand the stratigraphic components that define the subsurface, that means you can define the controls on fluid flow and contaminant migration. But without this understanding, we're basically just drilling blind. And that's where we get into the point that does support what Jim says, and that's, well, then the more holes we punch, the more we can understand. Well, that's the case when you don't have as good a predictive tool as what's really available to us. So this is the primary problem, because again, in some of my introduction slides, I showed how assume homogeneous isotropic conditions, map out the gradient, you get a good idea of groundwater flow, and that works to a certain degree. But the problem is the example I'm going to show you here, and that's when we do have truly aquifer heterogeneity that impacts groundwater flow and contaminant migration. The example that I'm showing here, this is an outcrop from somewhere in Ontario, Canada for scale. That's a person circled in red, and these are environment of deposition is fluvial, river environment, meandering fluvial deposits. And these are outcrops, so geologists are able to walk all around and really get a good understanding of 3D of this, okay? So of course, we don't have that luxury with the limited boring logs we have at our site, but we'll get to that later. So yeah, this is a facies model that helps provide a predictive tool for subsurface. And so I'll take you through this. This is a blow-up of that. And what we see generally here is that the gray, lighter color, that's coarser grain. Those are channel deposits, so they're mainly sands and gravels, whereas your browns are dark, that's silts and clays. And in this kind of depositional environment, the way things are deposited is not layer cake, one on top of the other. They actually accrete. In this case, there's a depositional dip, and that's from the left to the right. And what I did to accentuate these fine grain layers is show them in red, and they're actually very extensive. They're like sometimes over kilometers in continuity. So what you end up seeing is this sand body is really very compartmentalized, okay? But now let's think about how we might go about this in a more standard traditional way if we were to encounter this in the subsurface. And what we would do is, that's assumed groundwater elevation, so that's our our groundwater table. And what we would do is install our A wells, right? First encountered groundwater, 1, 2, and 3. And we would call that's our A zone, right? Well, you take a look at that, and in this depositional environment, you see that K hydraulic conductivity from left to right is extremely low. In fact, these wells are not even in communication at all. And if you don't know that going in, then your monitoring program, the subsurface chemistry data you collect, the groundwater elevations you collect are not going to lead you down a path of understanding of where your contaminants are going. And the important thing here is these, especially in this kind of depositional environment and a lot of others, this is more the rule and not the exception. So this is, again, to reinforce the importance of doing more detailed and high-level geologic evaluation of our data before we invest in our monitoring programs and our remediation designs. So now to the case study. This is basically how to fix it, and that's by releasing the power of our existing data. And this example is going to be a former semiconductor manufacturing site in the Silicon Valley, VOC groundwater plume that's commingling with neighboring sites. And this was in response, we were brought on to help with this project after a 5-year review by EPA responded that there was a need for more source remediation. So I'm going to show how we used environmental sequence stratigraphy to better define the contaminant migration pathways. So this is an example I showed earlier, and this was the existing original CSM that was the basis of the 5-year review. And that, again, showed that there was this issue about increasing TCE concentrations in what was considered down gradient from the on-site source. Okay, so what our stratigrapher did is first better understand what is the depositional environment. In this case, it's what's called an anastomosing river, similar to a meandering river. But what's important, I'll point out here, the couple important things here is, first of all, what's representative of channel deposits is, as I showed in that earlier example, these fining upward sequences. Because again, this is shown as coarsest grain to the right, sand and gravel, and then silts and clays to the left. So this vertical grain size pattern is representative of channel deposits in this depositional environment. And then the other thing you see is that these channels are encased in the dark color. That's the floodplain deposits, the silts and clays. So you have these channel, high permeability channel deposits that have a distinctive depositional distribution and also, dimensions. So what we did was create these graphic grain size logs like I described before, and this is a detail of the boring log to show that when you look at these, you end up with these fining upward patterns that are representative of these channel deposits. You see going from gravel to silty sand to sandy silt and silt and clay. So that's just a classic channel deposit. And then what we then do is plot all these graphic grain size logs, and more so than what you see here, we actually create a whole network of cross sections, and then interpret what you see, the interpreted channel deposits versus floodplain deposits, and this is a north-south cross section. And again, this is being able to, with the limited data existing data that we do have, actually map out the channel, subsurface channels. And this goes back, one of the things, at the depth of this was considered the B aquifer. So this was down somewhere between, I think, 20 and 40 feet below ground surface. And we defined two different channels, a shallower hydrostratigraphic unit and a deeper hydrostratigraphic unit, HSU2. And now what we we're then able to do is look at the chemistry data now once you have the geologic framework. And what you end up seeing is this is a chemistry plot that shows primarily TCE and DCE, PCE were at both of the source areas. But what differed was there was a lot of enhanced reductive dechlorinization that injections that happened at the source area. So contaminants that were representative of this source area, contaminant suite, had a lot of vinyl chloride versus the offsite that was not done. So vinyl chloride was not typical of the offsite. But what was typical of the offsite source was freon, and freon was not part of the contaminant suite for the onsite source. So let's look real quickly then at this HSU1, the shallower of the two, which goes through the on-site source. And what you see is vinyl chloride is in all of these groundwater samples. And then, except here, you see no vinyl chloride because that happens to be a well that was screened in HSU2, the off-site channel. And then when you look over at this one here, this hits both channels. So you get that characteristic freon that comes from the off-site, and as well as the VC that's representative of the on-site. So generally speaking, what that's saying is that this upper channel is what contains the on-site source contamination, and this lower channel, HSU2, is impact that's coming from off-site. And then what we end up, we're able to identify is that this is actually the contaminant pathway for the increased TCE that was seen in the down gradient well. And that would not be understood by just, again, what we saw originally, just looking at a groundwater gradient map and trying to predict based on that alone, without looking at and tearing apart the details of the geology. So again, that's the ESS-based conceptual site model actually was able to tease out the details and of this channel, which was responsible for the down gradient increase in contaminants. So this was an example where the issue was about trying to figure out sources. But think about anything you're doing. Again, putting together a monitoring program, trying to determine the right remedies to use. In all cases, you need to know the plumbing. So again, that's the good news, is we have the technology to improve, with existing data, our understanding of the subsurface, and this is critical for the success of our remediation. So how do we make geology more of a focus in our industry? First one there is I'm actually co-authoring a technical issue paper with EPA on environmental sequence stratigraphy as a best practice for CSMs. So that's one prong. Another thought is to require that 5-year reviews include upgrading CSMs with more geologic, modern geologic data analysis. Another is that when we're dealing with unconsolidated aquifers, that our project team should probably include experienced stratigraphers. And lastly, our regulatory agencies, they need to weigh in with more geologic expertise, and that would also help.